Hi everyone. In this video, we will be discussing the mean value theorem with the ultimate goal of proving the mean value theorem by the end of this video. To begin, we'll first look at a couple of intermediate theorems, which will then ultimately help us prove the mean value theorem. To begin, the first theorem we want to look at is theorem 2.27, also known as Fermat's theorem. There are many theorems named after Fermat, so you have to be a little careful here. But this theorem is in fact due to Fermat. The theorem says let f be defined on a closed interval AB with a local extreme point at C, where C lies in the open interval AB. By local extreme point here, we mean either a local maximum or a local minimum. Then, if f prime of C exists, f prime of C must be equal to 0. So this is a pretty common result. It's something that gets used a lot in Calc 1, although we often don't really think about it maybe in exactly the right order of things. So you can imagine you have some function some function on a closed interval AB, and maybe my function looks something like this. Okay, so there's a perfectly good function that's defined on the closed interval AB. What this theorem says is, if we are at some point C in between A and B, and C is a local extreme point. So if we look, here is a local maximum, here is a local minimum, here is another local maximum, here is another local minimum. Then what this theorem says is, if the derivative exists at that point, then the derivative must be equal to 0. So if I look here, my function is differentiable, derivative is 0. Here my function is differentiable, derivative is 0. Here my function is differentiable, derivative is 0. So these are all sort of confirming the result here. Here, my function has a corner. It's not differentiable here, so we can't say anything about the derivative here. Okay. Now, typically, the way we actually use this is sort of in reverse, although we have to be a little careful about that. The converse of this theorem is not true. It is not necessarily the case that if the derivative at a particular point is 0, then you're at a local extreme point, right? Take the simple example of x cubed, right? If I take x cubed and look at this function at 0, the derivative here is in fact 0, but we are not at either a local maximum or a local minimum value. So while the converse is not true, what we often do is we use places where the derivative is 0 or where the derivative is undefined to construct a set of points that we might check for local maximum and local minimum values, right? So often in Calc 1, right, you'll define the notion of a critical point. That class of critical points includes places where the derivative is 0, right? Also places where the derivative is undefined. And then you go start checking those to see if those happen to be local extreme points. That whole process works, however, because you know that every local extreme point has to occur either at a place where this fails, or so either the derivative doesn't exist at that point, or if the derivative does exist, the derivative must be equal to 0. So that class of critical points must contain all of the local extreme points, although there will be some points on there potentially that are not local extreme points. So this is a theorem that actually gets used quite a bit, not when talking about the mean value theorem, but when talking about optimization in Calculus 1. So with that little bit of background, let's see if we can take a careful look at this theorem. And it's actually going to turn out that we are going to do a lot of the heavy lifting for proving the mean value theorem here, even though we haven't stated the mean value theorem yet. So let's prove this theorem. Okay. So I am starting with a function that I know has a local extreme value at a particular point f. Let's go ahead and just assume, for the sake of argument, that we're at a local maximum. Okay. So assume, or without loss of generality, we're going to assume that f has a local maximum at x is equal to c. All right. Well, what does that mean? That means that f of c is greater than or equal to f of x for all x nearby the point c. Okay. So said another way, we can choose a neighborhood. So I'm going to choose a delta greater than 0 such that the delta neighborhood of C is entirely within the closed interval AB. I can do this because one of our assumptions about C, if we go back to the statement of the theorem, one of our assumptions about C is that C is in the interior of that interval. So C can't be an endpoint of the interval. If C could be an endpoint of the interval, we wouldn't be able to do this. Okay, so I'm going to choose a delta such that this neighborhood is entirely contained within this interval, and now we're going to use the fact that we have a local maximum at C. So we're going to choose this so that f of C is greater than or equal to f of x for all x in my delta neighborhood of C. Okay. So again, that's what it means to be a local maximum, right? I can find some neighborhood of C such that f of C is greater than or equal to all the other outputs that occur in that little neighborhood. Okay. All right. So now I want to sort of look at what's going to happen. I want to prove the derivative is 0. So I need to somehow analyze that difference quotient that's in the limit definition of the derivative. Okay. Now I'm also going to do that for reasons we'll see in a second. I'm going to look on either side of this little neighborhood. So remember that this neighborhood formally, right, since we're just in R, this is just the interval C minus delta to C plus delta. Okay. So let's first consider x values between C minus delta and C. Well, in that case, what can I say about f of x minus f of c over x minus c? Well, this top part, f of x minus f of c is a local maximum value. So this f of c will be greater than or equal to f of x. So this numerator piece here is always going to be non-positive, right? F of x is going to be less than or equal to f of c. So this difference, at the largest it could possibly be is 0, otherwise it'll be negative. If I look at the denominator, x minus c, let's see, I'm looking at x values that are less than c. So again here, this difference, this will actually be strictly negative. Okay. So what do I have here? I have non-positive over strictly negative. This quantity will be greater than or equal to 0, right? So for x values in this interval, this quantity must be greater than or equal to 0. Well, now let's look on the other half of that neighborhood. So now, consider x in the interval C to C plus delta. Well, then in that case, when we look at this quantity again, for the same reason as before, f of c is a local maximum. This difference will again be non-positive. However, now if I look in the denominator, x is bigger than c. So this will be strictly greater than 0. So now I have non-positive over strictly positive. Now this is going to be less than or equal to 0. Now, so far, right, all we've shown is that for this range of x, this value is greater than or equal to 0. For this other different range of x, x is less than or equal to 0. So far, no problem. It just happens that this one's it's greater than or equal to 0 when x is this range, and it's less than or equal to 0 when x is in this range. Okay. However, now we realize if I look at a limit from the left, okay, so I'm going to maybe sort of break this up here, okay, because this will line up nicely. So based on this part of the proof here, that tells us that the limit as x approaches c from below of f of x minus f of c over x minus c, this limit must be greater than or equal to 0. So for every x value close to c but below c, this quantity is greater than or equal to 0. So if you take the limit of a bunch of values, each of which is greater than or equal to 0, the limit must be greater than or equal to 0. And now if I look over here at the limit from the right, of this quantity, that value will be less than or equal to 0. Okay. So again, from this fact, we get this about the limit from the left, or the limit from below. From this fact, we get this about the limit from above, or from the right. Okay. Now, so far, everything's great. But what do we know? We also know that the full limit must exist because one of our assumptions is that the function is differentiable at c. So, since f prime of c exists, the limit from the left must be equal to the limit from the right. Well, I've got this quantity is greater than or equal to 0, this quantity is less than or equal to 0, and now because this is differentiable and therefore the full limit exists, these two have to be equal, which can only happen if they are both equal to 0. Okay. And so the full limit as x approaches c of f of x minus f of c over x minus c must be equal to 0, and that is by definition f prime of c. So you'll notice that in the whole first part of this proof, we're not actually using the differentiability yet, okay? So we're first just examining these difference quotients, and this all really just uses the fact that we have a local maximum at c. Okay. Now, what happens is here at the end, we use that to say something about these limits. Now, we actually first use the differentiability here to even know that this limit must exist, right? So this limit must exist because the function is differentiable. And since each of these is greater than or equal to 0, the limit must be greater than or equal to 0. Similarly, this limit must exist because the function is differentiable. Now I know that each of these is less than or equal to 0, so the limit of a bunch of things that are less than or equal to 0 must be less than or equal to 0. Now, furthermore, since the limit exists, the limit from the left and the limit from the right must be equal to each other, and therefore they both have to be 0. That's the only way both of these could be satisfied and be equal to each other, and therefore the derivative is 0. Okay. Now, this is, a very sort of analysis-y type of proof. I mean, you're chasing the definitions through, you're using facts about local maximum and local minimum values, right? We analyze carefully some limits. This is very much an analysis, just getting down to the definition type of proof. Okay. What we're going to see now is that moving forward, to get to the mean value theorem, we're basically just going to invoke this theorem and deal with some special cases that won't be quite so difficult to deal with. And once we do that, we'll have the full proof of the mean value theorem. All right. So before we get to the mean value theorem, one more sort of intermediate version, which is Rolle's theorem. So suppose f is a function mapping from the closed interval AB into R. And let's assume three things about f. Let's assume that it is continuous on the closed interval AB. It is differentiable on the open interval AB. And the function values at a and b are equal to each other. So f of a is equal to f of b. Then Rolle's theorem says there exists some point c in the open interval AB such that f prime of c is equal to 0. Okay, so visually, right, if we sort of want to have a mental picture of this. So here's my closed interval AB. My function is continuous and differentiable on here. And my function values are the same at both endpoints. Then Rolle's theorem says, right, I must have some point C where my derivative is 0, right? Now, notice here, right, it just says there exists a point, right? We can see here that there are actually several, okay? But typically this is an existence type of theorem. They only say that something exists, not usually how many there are. That's usually a separate question we call multiplicity. So this doesn't say anything about how many we have, just that there has to be at least one. Okay, there could be many, there could be only one, there could be exactly 10. We don't know. Under these conditions, all we can say for certain is that there is at least one. All right. So in order to prove this, the first thing we want to do is think, well, how could I use Fermat's theorem, right? So what did Fermat's theorem say? Fermat's theorem said if you have a local extreme value, so a local maximum or a minimum, then you know that the derivative, and if that point occurs in the interior of your closed interval, then if the function is differentiable at that point, the derivative must be 0. Well, if I start to look at this, okay, I'm already assuming continuity and differentiability in the whole interval. Since it's continuous, I ought to be able to use the extreme value theorem, which tells me there's a local maximum or a local minimum value somewhere in the closed interval AB. And then, well, if that point happens to be in the interior of the interval, I can use Fermat's theorem. If it's not, I've got to do something else. So that's going to be actually the basic structure of our proof. We want to use the extreme value theorem, but we need to be careful about where these points are going to, from the extreme value theorem, are going to end up lying in our interval. All right, so to prove Rolle's theorem, we will first, we first just need to set up a few things. So again, we want to apply the extreme value theorem. So since f is continuous on the closed interval AB, then by the extreme value theorem, there exist points x sub little m and x sub capital M in the closed interval AB such that f of x sub little m is equal to the minimum value over all x in AB of f of x, and f of x sub capital M is equal to the maximum over all x in AB of f of x. All right. Now, again, if these are actually global maximum and minimum points, so global extreme points. If even one of them lies in the interval, in the open interval AB, then I can use Fermat's theorem and I'll be done. Okay, so let's actually break this out then into cases. So if at least one of x sub little m, x sub capital M are in the open interval, let me then set that value to be C. So the idea is you can imagine maybe just over here, interval AB. Let's say you have a function that looks like this. Now, your x sub capital M is actually at the endpoint, okay? But x sub little m, where the minimum occurs, is in the interior. So we're just going to call that our point C. Okay, you can imagine if you sort of flip this graph upside down, right? You'd get the reverse situation where the minimum value would occur at the endpoint and the maximum value would occur in the interior. You can also, of course, come up with examples where both the maximum and the minimum are in the interior. In this case, I just need one of them to be in the interior for this part to work. So in this case, then, okay, I'm setting C to be the one that is in the open interval. So C is in here, and C is a local extreme point. Now, we're assuming that our function f, one of our hypotheses of Rolle's theorem is that f is differentiable on the open interval AB. So f must be differentiable at C. And so since f is differentiable at C, then by Fermat's theorem, we have found our point C such that f prime of C is equal to 0. All right, that's case one. All right, well, what's case two? So I need to cover all my cases. This covered the cases where at least one of the points, x sub little m and x sub capital M, were in the open interval. So the only other case I need to consider is what happens if they're both at endpoints. Okay. So suppose x sub little m and x sub capital M are both endpoints of the interval AB. Okay, so they could both be equal to A, they could both be equal to B. One could be equal to A, one could be equal to B. Without loss of generality, let A, so let the minimum value occur at the left endpoint and the maximum value occur at the right endpoint. So let's see, what would that look like? So you might think about, okay, I need the minimum value to occur at the left endpoint, the maximum value to occur at the right endpoint. So you might sort of come over here and say, oh, I could have something like this. right? That'd be minimum value at the left endpoint, maximum value at the right endpoint. But there's one hypothesis from Rolle's theorem we haven't used yet, which is that f of a has to be equal to f of b. So you start thinking about that, well, how would that work then, right? That would mean that the maximum and minimum value, if they're both at endpoints, they have to be the same. The only kinds of functions that have maximum and minimum values that are the same are constant functions. Okay. So how do we carefully sort of write this notion out? Well then, the minimum of f of x, and I'm going to drop the over the interval ab, but just sort of assume there. The minimum of the function is equal to f of x sub m, which is really f of a, which is equal to f of b. F of b is really just f of x sub capital M, but that's the maximum of the function f of x. And so again, you have the minimum value and the maximum value of f of x are equal to each other. And hence, f of x is constant and, for example, must be equal to the value at the left endpoint, which is the same as the value at the right endpoint, however you want to write it. But if f is a constant function, then f prime of x is equal to 0 for all x in AB. Okay. And so pick any points you see you want. So let's see, be any point in the open interval AB, and f prime of c will be equal to 0 as desired. So what we see here essentially, right, these break us up into two cases. The first case is where we can use Fermat's theorem. So the first case says, okay, under the hypotheses of Rolle's theorem, by the continuity, you must have a local maximum, or you must have an absolute maximum, absolute minimum value that are achieved on your interval. So in case one, they say, well, hopefully like at least one of those would be in the interior of the interval. If it's in the interior of the interval, we can apply Fermat's theorem, and that gives us that the derivative at that point, at that absolute maximum or minimum value, must be 0. But there is this tricky case where the maximum and minimum could occur at the boundaries, right? So now you don't have any interior maximum or minimum values. But in this case, because Rolle's theorem assumes that the function has the same value at both boundary points, the only way that can happen is if the maximum and minimum values of the function are equal, which means that your function must have been a constant. And the derivative of any constant function is 0. So pick any point you want in the interval, the derivative will be 0. Okay. Now, again, Rolle's theorem is a nice theorem. It's helpful, but again, our goal is to prove the mean value theorem. And so in order to prove the mean value theorem, we need to figure out how to sort of adapt Rolle's theorem to help us in that specific case. I have new markers, which are hopefully showing up much better, but they are also a little more difficult to erase. So having to use some of the cleaner to help me here. All right, so finally, to our statement of the mean value theorem. Now, the first thing you'll see is that this says Lagrange's mean value theorem. There's actually another version of the mean value theorem called Cauchy's mean value theorem, which we'll talk about in a later video. But Lagrange's mean value theorem is the statement of the mean value theorem you would have encountered in a calculus course. So it says simply, suppose f from a to ab into r is continuous on the closed interval and differentiable on the open interval. So notice these first two look just like the hypotheses from Rolle's theorem. We've dropped the third condition. Okay. Lagrange's mean value theorem says, then there exists a point C in the open interval AB such that f prime of C is equal to f of B minus f of A over B minus A. Now, the first thing to note, right, is if you also assumed that f of A was equal to f of B, right, then that would imply that there was a point f prime of C, right? This would then be 0 if f of B was equal to f of A. So the first thing to note is that this really is a generalization of Rolle's theorem. It includes, as a special case here, Rolle's theorem. So that's one thing to note. Now, visually, what's going on here, the standard picture, right, we would draw in a calculus course. Okay. So if I look at, here's a function that's continuous on the closed interval, differentiable in the open interval. This quantity on the right-hand side is the slope of the line between these 2 points. Okay. So this line here has slope of f of B minus f of A over B minus A. It's the slope of the secant line between the point A, f of A, and B, f of B. What this says is there has to exist some point C, okay, and my drawing skills are not always the best, so let's try, maybe it's about here. There's one. So if I were to take the derivative at this point, right, it would be the same, this tangent line would have the same slope as this. Now, I'm not a great artist, so maybe this doesn't totally look like it. There are actually more points here, right? So if I took one here or somewhere around here, right, I would also find values where the derivative at this point, which I can think of as the slope of the tangent line, is the same as this pink slope, or the slope of this pink line here, okay? Now, again, in the case of Rolle's theorem, these points are at the same height, so the slope of that line is 0. Okay, so you hopefully see, again, this is just this includes, as a special case, Rolle's theorem. All right, so let's see how we prove this. This is a really clever and sort of the first time we're going to see something like this in this course, although we'll see it again later. To prove this theorem, we're actually going to introduce an auxiliary function. Now, when you hear people talk about auxiliary functions, usually those aren't things that are like well defined. Often they are functions that are specially created to help cleverly solve a problem. Okay, so let's see how we're going to use that here. So again, I'm going to start this proof by defining a function. I'm going to call this function phi. It's going to map from the closed interval AB into R. And I'm going to define it in the following way. I want phi of x to be equal to f of x minus f of A minus f of B minus f of A over B minus A times x minus A. Now, you're probably looking at this right now, and this seems totally mysterious, right? I just wrote down some big expression, okay? In a little bit, I'll show you sort of why this is the right function to consider. But for now, I just want to see that this function works. I think it's sort of cool the first time going through this, because you just go, wow, why would that possibly work? And then once you study this function a little bit more, and I'll show you again in a bit, you go, oh, okay, it makes sense that this is the function that would help me here. Okay, but let's first just note a few things about it. So note that the function phi is continuous on the closed interval AB. Okay, why is that? Well, what is phi? It's made up of f. That's a constant. That's a constant, right? That's an x minus a constant. Okay, so phi of x is just the sum of a continuous function, a constant, And this is a linear factor, the linear polynomial, which is continuous, times a constant. That will still be continuous. So it's just a sum of continuous functions, each of which is continuous on the closed interval AB. So phi is continuous. Phi is differentiable on the open interval AB. Now, again, for exactly the same reason, f is differentiable on the open interval AB. That's a constant. That's a constant. That's a linear polynomial, right? It's differentiable, okay? So phi is continuous on the closed interval AB. Phi is differentiable on the open interval AB. And let's look at phi of A. If I plug in A for x, I get f of A minus f of A. Well, that's 0. And then I get minus this constant times A minus A, but that's 0. Constant times 0 is 0. So phi of A is 0. What is phi of B? If I plug B in here, I get f of B minus f of A. If I plug in B here, I get B minus A, but that'll cancel with the B minus A here, and I'll be left with f of B minus f of A. So I get f of B minus f of A minus f of B minus f of A, which is 0. So I get that phi is 0 at A and B. Well, now you might be starting to see why at least phi is a good choice of function. Phi now satisfies all the hypotheses of Rolle's theorem. So I can apply Rolle's theorem. So by Rolle's theorem, there exists a C in the open interval AB such that what? Such that phi prime of C is equal to 0. Well, what is phi prime of C going to be? Well, what's phi prime of X? If I just come up here and ask myself, okay, what is phi prime of X? Okay, that'll be f prime of X. That's a constant. Its derivative is 0. And here, I'm going to have a minus this constant times X. Okay, the derivative of minus a constant times X is minus that constant. And then I have minus a constant times a constant. That's still a constant's derivative is 0. So here's the derivative, phi prime of X. Phi prime of C then will just be f prime of C minus f of B minus f of A over B minus A. And again, by Rolle's theorem, that's going to be 0. But now if I look at these parts, if I just move this over, I get precisely the result I want. Now, to help us understand sort of geometrically what's going on here, we want to actually go back and examine this function a little more closely. And in order to do that, what I want to do is flip over to Desmos, and let's look a little more closely at what's going on with this function by looking at a particular example, which I think will help make a little more sense of exactly how this proof is working. So to understand what's going on with this function phi, let's just consider the following function f of x. Now, we don't need to worry specifically about how this function is defined. I basically just created something that would wiggle around a little bit so we could see what was happening. So we have a function here, f of x, defined on some interval ab. And the idea of the mean value theorem is I want to show that there is some point C such that f prime of C is equal to f of B minus f of A over B minus A. But I want to prove this by using Rolle's theorem. So we construct this auxiliary function phi, which I want to satisfy the property that phi of A should be equal to phi of B, which I'd both like to be 0. I don't need them to be 0, I just need them to be the same in order to apply Rolle's theorem. But while I'm doing this, I might as well just make them both 0. So the idea is that this function phi is constructed, and you can see over here I've constructed it just as we did in the proof, but I've actually added in these parameters s and t. So right now s and t are both set to 0, and with that, right now phi of x is just f of x. So if I turn on the graph of phi, it'll show up in blue, and you'll see it actually just lays directly on top of the red function f of x. Okay, so right now phi is just exactly the same as f of x. But now what I want to do is I want to see what happens as I change the values of s and t from 0 to 1. So let's first see what happens as s moves from 0 to 1 with t left at 0. So if I move s from 0 to 1, what's going to happen, right, is I'm basically transforming my function phi from f to f minus f of a. So what I'm really doing is I am shifting my function now so that f of a is equal to 0. Okay. Now in doing that, I've also changed, so that phi of a is equal to 0. So I've taken my function f and I've just shifted it up to create this function phi, which has phi of a equal to 0. But you can see right now this is just a shifted version of f, right? I've just shifted f so that this transform function will be 0 at a. Now this t value, as I transform t from 0 to 1, it is going to take my function and basically compress it in a particular way. It's not a pure compression like of the output values, but it's going to compress this so that at b, this function is now 0. Okay. Again, if I go back to 0, and now this shrinks it down so that phi of b is 0. Now, with that, what we then do in the proof is we say, okay, well, now I have a function phi, so that phi of a is equal to phi of b is equal to 0. And phi is both continuous on the closed interval AB and differentiable on the open interval AB. I can apply my previous Rolle's theorem, which tells me that there must be at least one point. Let's take this point that I've identified with a green star here, where the derivative is 0. Okay, so that's applying Rolle's theorem. And then what we show is that if we apply Rolle's theorem to phi, and you can sort of backtrack this, watch what happens to that point. Now, if I transform everything, the tangent line included, right, this will now transform right back to a point, right, whose derivative is equal to the average rate of change of this function over the interval. So this is exactly the point that I wanted for the function f. It's just I was able to identify it through looking at properties of the auxiliary function phi. So hopefully that helps clarify this function phi. It seems very strange initially in the proof. It works, you can verify it. It seems strange, but really it's motivated by this geometric intuition of wanting to transform the function f into a different function which will satisfy the hypotheses of Rolle's theorem, so that we can then apply Rolle's theorem, and then essentially by transforming back, we get the point that we want for our function f. So now hopefully that helps explain where the function phi comes from and exactly how we prove Lagrange's mean value theorem using Rolle's theorem. In the next video, we'll look at more properties of differentiable functions before moving on to understanding higher derivatives and Taylor's theorem.